there's something. All right, so this is a short introduction to cosmological structure formation. So we know that the universe is homogeneous and isotropic on large scales. That's something which we all know. But we also know that there are inhomogeneities and structures on small scales like galaxies and clusters of galaxies. Now, roughly the scale on which the homogeneity and isotropy principle, which is also known as the the cosmological principle. So if you look at the cosmological principle, it essentially applies to large scales, which is typically the 100 megaparsec or larger. Then, of course, we have a very simple description of cosmology, and this is something which I think most of you are familiar with. Now, we are not going to go into the details of the background cosmology as it is known, because our focus will be on inhomogeneities on small scales and how these inhomogeneities grow and form the kind of structures that we see. Okay, so but there are some important aspects of the large scale picture, the homogeneous and isotropic universe, which is also known as the background cosmology. And so we have few observational evidence, the crucial ones. One is, of course, the universe is expanding. We have the Hubble's law. And we also have to incorporate this Hubble's law into the framework of a homogeneous and isotropic universe. So there is only one kind of expansion which is possible. So the Hubble's law has to be consistent with the principle of homogeneity and isotropy. So with that, we have the description on these on large scales. Of course, in the framework of general relativity, we have the description in terms of what is known as the Friedmann-Robertson-Walker metric. And if you remember what this looks like, so the metric for the homogeneous and isotropic spacetime is given by ds square GAB dxa dxb. And this is given by c squared dt square minus some spatial line element, which we write as d sigma square. And this spatial line element is some gamma mu nu dx mu dx nu. So because we have homogeneity and isotropy, we have to understand what this time really means, the coordinate t that we have used. So we are essentially talking about hypersurface of constant curvature, and we are labeling these hypersurfaces of constant curvature by a label t. And on that space-like hypersurface, which is a constant curvature hypersurface, the line element is given by this gamma mu nu dx nu. So this is a three-dimensional space which has constant curvature. It's a maximally symmetric space. And we know that only three possibilities are there for this spatial metric to be. So it can be flat, it can be spherical or hyperboloid. And then what the general prescription is, we take a metric of this form. And of course, one has to understand that this gamma mu nu that we have has to also incorporate the expansion. So this has the form some a square, this times t, times some metric, which is the three-dimensional metric of a constant space. Okay, now the curvature of this space, which is k, can take up values, as you know, 0, 1, and -1, depending on what kind of geometry we have. But you can clearly see that this metric is completely specified if you know this function a of t and the value of k, all right? And then if you use Einstein's equation to see what kind of equations you have for the scale factor, then we have these background equations, a double dot by a. These shall be important, so I'm just writing down these familiar equations. These are all known to you before we move on to structure formation. -4/3 pi g rho plus 3p. It's very important to see that the pressure actually appears as a source term in general relativity. And then you have the other equation, a dot plus k by a square equals to 8 pi g rho by 3. Along with this, we have the conservation of energy momentum, which gives you dDA of rho A cube equals to minus 3 P A square. And if you have a certain component which has an equation of state, rho, okay, P equals to some W times rho, then we can immediately see that using this, it follows that this rho will have an evolution, rho naught A0 by A to the power 3, 1 plus W. These are all known results. I'm just writing these down for our use. So, so what the paradigm is that we have different components of the universe, namely dark matter, baryonic matter, and radiation and dark energy. And they have different densities and pressures and different equations of states, and each of them evolve according to the densities evolve according to this, and then you can solve the equations for these equations for either a universe containing one component or multi-component. So that's the standard procedure, the standard picture. So we define the Hubble parameter, which is A dot by A, and then one can write down the expression for the Hubble parameter H squared as H naught squared. And then for different components, if you have different densities, then you can write this down as a summation over omega I0, A to the power minus 3, 1 plus Wi. I corresponds to different kinds of components, plus 1 minus summation omega I0, A to the power minus 2, where we have defined this omega I0 as rho I, the density of the ith component, and the present time divided by something called the critical density, where rho critical is 3 squared by 8 by G. So I'm not going into the details of this because this is background cosmology and I'm sure everybody is familiar with this. Now this describes the universe which is homogeneous and isotropic. So we have the description in terms of a fluid with our energy momentum tensor, and then we have Einstein's equation for the FRW metric, and then we have these equations, and when we solve this, we get the evolution of the background universe. Now, of course, if you try to do the same for the clumpy universe, we cannot definitely write this metric. So the general procedure is that we work in the framework of perturbation theory. So we assume that there are tiny perturbations to this background, and due to some mechanism, namely gravitational instability, these tiny fluctuations grow and they form the kind of structures that we see. That's the basic paradigm within which we function. So we start with perturbations of the metric. So what one should do in the true sense, in the real picture, is that start with a metric, the same background metric of the FRW universe, and perturb these metrics. So you have these 10 components of the metric tensor. You perturb each of these components and then write down the Einstein's equations. Einstein's equations can be then split into the background and perturbation terms. And then you similarly perturb the energy momentum tensor with a background and a perturbation. And then you look at how what are the equations for the perturbations. Now, this is what is called relativistic perturbation theory. Now, there is one important problem in trying to do that, and that is the fact that in the background cosmological framework, there is this universal definition of this time coordinate because there are these space-like hypersurfaces which are of constant curvature, and on those surfaces you have constant density, pressure, everything. And then you have these slices, and at each slice, each spatial slice, you have constant curvature. Now that is something which you don't have in the perturbed universe because there is no homogeneity anymore. Now, since you cannot identify these hypersurfaces, we cannot define universally something like a time coordinate as we could easily do in the case of the background. So you have to choose some kind of a coordinate system. You have to somehow choose, you have to slice out your universe and then put these labels of time. But the choice is up to you, and that gives rise to the possibilities of, now if you choose a certain time slice, there might be emergence of fluctuations which are not real. It just might be the virtue of your choice. So in general relativistic framework where we do perturbation theory, one has to be very careful because there might be perturbations which might appear just due to an artifact of a choice of coordinate system. Now, of course, there are ways out of this. So one can choose what is called a gauge invariant formalism, where we can choose certain quantities which are actually independent of the kind of gauge choice that we make. But that's a rigorous formalism. Now, in this course, in this short course, we are not going to take the relativistic route. Now, the reason is as follows. Firstly, what are we aiming to do? We are trying to look at 21 centimeter physics, which is related to the neutral hydrogen. And the redshifts of interest, as you heard from Somnath's lecture today, is from redshift 200 to redshift 0, right? So that's the kind of redshift regime that we're interested in for the purposes. Now, of course, the universe is clumpy, but at these redshifts, when will relativistic effects really be relevant? Now, it turns out relativistic terms, when you do the full relativistic perturbation theory, the relativistic corrections to a non-relativistic formalism, which we shall do, will occur only on very, very large scales, on what are called super horizon or scales which are the size of the horizon. Okay. Now, if you're interested in scales which are much lesser, much smaller than the Hubble size, the size of the horizon size, then those terms which are relativistic in origin, because on those large scale relativistic effects come into play. Now those terms will be highly subdominant, and we would not require them at all for most of our purposes. The kind of scales we are interested in probing would be much smaller than the kind of Hubble size that we have at those redshifts, and thereby those relativistic terms will not really contribute much for our purpose. So given that, instead of going through the details of relativistic perturbation theory, we will actually do what is called a non-relativistic perturbation theory or Newtonian perturbation theory. And whenever there would be a requirement to sort of get some intuition from the relativistic theory, we will bring it, but mostly we will fix ourselves to our understanding of structure formation using Newtonian physics. So what is the description that we have? We have a fluid description. So we have a cosmological fluid, which is described by a density, the velocity. Now let me use capital letters for this, and pressure. So these are the quantities of interest in a fluid, and we have to write the fluid equations. Now you know what the fluid equations are. So we have the equation of continuity, which is conservation of energy, mass. I am sure most of you are familiar with this. Then you have the Euler's equation, which is basically the force equation. Now you see this pressure gradient offers like a force, and then you have, of course, the force coming from gravity. So this is gravitational potential phi, and then finally you have the Poisson equation for phi, del square phi equals to 4 pi g rho. So you have these five equations which we are interested in solving. Now, these are the fluid equations, but please understand we have cosmology. So universe is expanding, and we have to write these equations in an expanding universe. And please understand this rho, v, and phi, p, all these are now quantities which are no longer constant. They have fluctuations at a given instant of time. So at a given instant of time, we have these rho, v, and p as having background contribution and then perturbation. So we will then try to work out a perturbation theory. Now, the first thing to do is to write these equations in an expanding universe. These are our standard fluid equations. You can see that your background equations, the Friedman equations, can be obtained from in an equivalent way from these equations, these fluid equations, and the Poisson equation. But here, what we shall do is we shall first write it down in an expanding universe because we are trying to do cosmology. So we introduce the scale factor in a very traditional way. So this physical coordinate r would be related to the co-moving coordinate through a scale factor, a of t times a co-moving coordinate x. And then this v, which we wrote, which is r dot. We'll have two terms, a dot x plus a x dot. Now you see, we had defined this x as a co-moving coordinate. So what does this term mean? Now this is, the first term is basically the Hubble expansion, the Hubble law, right? Because you can just divide it by a and multiply by a, and then you just have v proportional to d. Now, what is this additional term? It says that there can be a piece, which is this x dot. So this is a non-Hubble flow, non-Hubble velocity, and this is what is called the peculiar velocity. So it's a deviation from the background Hubble expansion. Okay, great. So that's our change of variables. We want to write everything in terms of this co-moving coordinate x. So these gradient operators, which are in the standard equation, are written in terms of the physical coordinates. This you have to write in terms of the co-moving coordinates. And so that is very simple. So this gradient with respect to r, this is basically 1 by a, because every coordinate gets scaled by a times gradient with respect to the x. And I'm going to drop this x suffix very soon because we'll be only working in these x coordinates. But there's also one more change that you have to do, which is to understand this t, this derivative with respect to t, that also has to change, because in these partial differential equations, you have the t appearing. This del rho del t is assuming that we are working in that r system, so it's at constant r. But r is now a function of x through this a. So we have to change this time derivatives as well, and that is pretty straightforward. You have to just use chain rules of partial derivatives, and you can take a function for any general function. You can immediately see that del f del t at constant x is will be related to del f del t constant r plus r dot grad r of f, standard partial derivative, and then this you can write down as a dot by a. This 1 by a comes from this grad r being converted to grad x, so grad x f x dot. So that's what you have. So that's again one of the things that you have to incorporate. So del del t r has to be replaced by del del t at x minus a dot by a x dot grad x. So this is a transformation that we have to do along with this. And then we have to write down the fluid equations, which will convert the fluid equations to equations in an expanding background. Okay, great. So let's do one, and then the remaining I will leave as an exercise. So let's write down the equation of continuity. So you have del rho del t plus divergence of rho, this is capital V, mind you, equals to 0. So you write this as del rho del t. So you change the minus a dot by a x dot grad x rho plus 1 by a divergence of rho, and then you have to write this v as a dot x plus the peculiar velocity, which is small v, equals to 0. Now, if you simplify this, what you would get is the following. You would get del rho del t plus 3 a dot by a plus 1 by a divergence of rho v. Now this is the peculiar velocity equals to 0. Similarly, if you work out the Euler equation, you would get this a double dot x plus del v del t. Again, this is the peculiar velocity plus a dot by a peculiar velocity v plus v dot grad v by a equals to minus grad p, capital P, by a rho minus grad phi by a. And also you have the Poisson equation, which now becomes del square phi equals to 4 pi g a square rho. Now let's pause here for a while. So these are basically our standard fluid equations in an expanding background. The A is to be determined from solving the background equations. And then you have this general set of equations. Now we have not made any assumptions about what is rho and what kind of perturbations it has, except that this V is basically now a non-Hubble velocity. It's a peculiar velocity. Okay, great. So now what we want to do is we want to take these equations and start looking at how we can apply perturbation theory. So what we do is we recognize that the density field rho will have a background contribution rho bar. Now this is the rho bar which appears in your Friedman equations for the evolving background universe. So you remember that the rho in your Friedman equations was only a function of A. It was only a function of time. Why? Because it was a constant on a spatial hypersurface. So that's what we write, rho. And the spatial dependence now is contained in a fluctuation. So we write introduce a fluctuating field. So this delta rho will now depend on x and t. Okay. So this is a fluctuation. So what one writes is we usually write it in terms of what is called a density contrast. So we write this as one rho bar. So where this delta is delta rho by rho. So this is called the density contrast, a quantity of profound importance in our analysis. And we shall see what does this make. So this is basically a fluctuating field, okay, which is on top of the background rho bar, and that gives you the density of the cosmological fluid. Okay, we can also write the pressure as a p bar, plus instead of writing a delta p, we usually use the symbol small p. And this is a fluctuation. And similarly, phi, the perturbation in the potential, this is equal to phi bar plus small phi. So these are our these are our physical quantities of interest, and we have split them into a background term plus a perturbation. So what we do is we want to write the equations, the fluid equations, in terms of these fluctuating quantities. And when we do it's just simple substitution, then the equations become the following. So you have, of course, when you put these equations back into the fluid equations, you have to recognize that you have to apply the equations for the background, and you have to substitute the background equations as well. And once you put that, then it simplifies, and you would have these equations. Delta, this is very simple, so I'm going a little fast because we'll discuss some important matters once we have the basic formalism ready. So delta del t plus 1 by a divergence of 1 plus delta v equals to 0. That's the first equation. Then we have del v del t plus a dot by a v plus v dot grad by a v equals to minus grad p. Now this is the small p divided by a rho bar 1 plus delta minus grad small phi by a. And then you have del square small phi equals to 4 pi g a square rho bar delta. Now, okay, These are the same equations which you would get from relativistic perturbation theory for a very specific choice of coordinates, specific choice of gauge, only under the assumption that we are working in extremely small scale limit. So what you do is you write the relativistic equations, not this Newtonian formalism, you write the full general relativistic thing and you choose a certain gauge, a very interesting gauge. And then in that gauge, what you can do is you can take the limit of very small scale fluctuations. So you are interested in very small scales. All the horizon order terms, the terms which make dominant contribution on the size of the horizon, if you drop those terms, then you would get these equations. Now, another important crucial difference from the full relativistic formalism and a Newtonian formalism is the role of pressure. Now, in relativistic formalism, you know that when you write the full energy momentum tensor, then the pressure has the same role as density. Now, that is not true in a Newtonian picture, right? So wherever you have pressure, for example, you think of studying, radiation, which we are not going to do so much. But if you study radiation, there's a strong, the pressure is 1/3 the density. So there one has to be extra cautious, and probably it's more reasonable to use the full relativistic formalism, because the pressure does not appear as a source in the Newtonian formalism, right? So that's something we have to keep at the back of our mind. Okay, now you see these are nonlinear equations. You have delta times V, and all these are nonlinear equations. And in the these nonlinear equations are coupled, and you can solve them on a computer and that is exactly what I think Avinash is going to talk about today. So when we simulate the density field, these are the governing equations of motion that we work with. Now you see there is phi, which is there is V, there is delta, but you see there is this P. Now these equations really don't close within itself, because you need to supply the P. Now for a component of the universe which has pressure, then you have to also supply some relationship of P with delta, usually in form of an equation of state. Now, once you are provided with that, then you can actually solve these on a computer numerically. Okay, so that's the standard prescription. You don't have to linearize it or do anything. Start with these nonlinear equations which depict the evolution equation of density fluctuations, okay, and velocity fluctuations and potential fluctuations in the Newtonian limit of small scale fluctuations. Okay, so there is no linearization yet. Now, of course, for analytic reasons, and of course, if you are interested in very small fluctuations, of course, these fluctuations grow, and we want the fluctuations to grow, because the whole idea is that if there is some seed of fluctuation, we are not going to talk about where the seeds of fluctuations come from. If you are given some seeds, then we expect that these seeds grow under this gravitational instability, the processes determined by these equations, and they would give rise to collapsed objects, namely galaxies and other kinds of structures. So the clumpiness of the universe can then be explained. However, if these fluctuations don't grow, then we cannot have structure formation. So eventually the fluctuations will grow, and once they grow, they will become large, and the linear approximation will fail at some stage. Now, if you're studying, for example, CMBR, now that is at Z equals to 1000. Now that the fluctuations are very, very small. The fluctuations in the CMBR temperature is of the order of 10 to the power minus 5, right? So it's very tiny fluctuations. And so the CMBR theory is essentially linear. So you don't have to worry about nonlinearities. Now, when you study 21 centimeters, you have the dark ages, which is redshift all the way up to 200, where fluctuations are still linear, but they grow. And in 21 centimeters, we shall also be interested in redshifts all the way up to redshift 0. So through reionization and then post-reionization, when these fluctuations will eventually become nonlinear. So for 21 centimeters, we can use linear theory at large redshifts, but we also have to be very, very careful about using linear theory and extrapolate it when we are looking at low redshift universe. So that's why the strong relevance of numerical simulations for the 21 centimeters, because we have to really ourselves in these equations in their full nonlinearity when we are talking about 20 centimeters, especially at low redshifts. However, we can still achieve a lot and get a lot of insights from the linear theory. So what we do is we linearize these equations. So when you linearize, you neglect all terms which are, say, for example, delta and v, both are small, so and delta square and v square. We drop all these terms which are higher order in these fluctuations. And after you linearize, you are left with, so linearized. Now we are working with linear theory. We shall see later what kind of statements we can make about weakly nonlinear situations towards the end of these lectures. We'll talk a little bit about quasi-nonlinearity or almost weakly nonlinear situations where delta is not very, very high, but they're approaching nonlinearity. So we'll have some time to discuss that. But right now, let's do the simple thing, which is studying fluctuations at the linear level. So you have del t plus divergence of v by a equals to 0. These equations look very simple, but they have a lot of insights. So let's write them down. Del v del t plus a dot by a v equals to minus grad p by a times rho bar. You see that 1 plus delta is gone, minus grad phi by a. And you have del square phi equals to 4 pi g a square rho bar delta. So these shall be the equations that we shall be interested in. Okay, great. Now what one can do is, instead of taking these equations, one can combine them and write a second order. So one can combine these two, and you can take the divergence of the second equation. So you will get divergence of v here and divergence of v here. And then you can substitute divergence of v from the first equation in terms of the derivative with respect to delta. And you will have a del square phi when you take the divergence, and then you can substitute again from this third equation, you can substitute del square phi. So you will get an equation only in delta. So we will first look at delta, and then we will look at the peculiar velocities. So the equations on you, once you do that substitution, you get one second order equation for delta, and that is delta double dot plus twice a dot by a delta dot equals to del square p pi a square rho bar plus 4 pi g rho bar delta. So that's our equation. Okay, great. Now, we have not spoken about this delta or this v much yet. We have just told that these are fluctuations, right? Now, this delta has a spatial part. It depends on space. And of course, it has to depend on space because it's a fluctuation. And it comes from a fluctuation on top of a constant density on the t equals to constant surface. So now these are fluctuations. So it has a space dependence. Now, this differential equation that you have is a time equation. It's an equation involving time derivative. So we are interested only at this level, the evolution or time evolution of fluctuations given some initial fluctuations in a background universe dictated by some law of Hubble expansion in the linear limit. So you see, there are a lot of things that we're talking about. What does this equation have? We are talking about first of very small scale physics because we have thrown out all sorts of relativistic effects. So we are looking at scales which are much smaller than the Hubble horizon. And then we are looking at growth of fluctuations. We are not looking at the spatial distribution of fluctuations, the growth or decay, whatever, evolution of fluctuations in a background universe, okay, in the linear regime, in the linear limit. So that's what this, so please be careful about this equation. Now, this delta could be fluctuations. Now, you know that there are different kinds of, so you have matter, so you have dark matter, you have baryons, if you're interested in matter. So you can write an equation for matter, and you can write it for baryons. So let's first work it out for dark matter, which is going to be simpler because we wouldn't have to worry about the pressure. Okay, so if you write it down for dark matter, then you can just write this for dark matter. Rho bar dark matter. However, if you can write it for baryons, but there's one important thing that you have to note over here. So if you look at the Poisson equation, del square phi equals to 4 pi g rho bar times delta. Now, all sorts of matter would contribute to the potential, right? So you would have rho dark matter times delta dark matter plus rho bar baryons times delta baryons. So you would have both these contributions. Now, if you go back to your background cosmology, you would recognize that this is much smaller than this. So what we are essentially going to say is that though the potential, the gravitational potential is sourced by both dark matter and baryons, this is so tiny that this phi is dominantly sourced by just dark matter. So on the right-hand side, even when you write this equation for baryons, as we shall see, this term on the right-hand side, you will have a pressure for baryons. But on the right-hand side, you would still write rho bar, dark matter, and delta dark matter. So on the left-hand side, you would have baryons, but on the right-hand side, you would have rho bar for dark matter because this is very, very small. Okay, but anyway, we'll talk about baryons later. Now, what we are going to talk later is the spatial dependence. So the fluctuation, when we talk about a fluctuation, we are talking about the spatial fluctuations, right? So that's something which we are not talking about. So there is some delta of x at some time t. This equation tells how it evolves in time, starting at some t equals to 0. So let's work it out for. So we are interested in solutions to this equation. Now, of course, you can just substitute. You can just sort of substitute h of a for a given background evolution and put this on a computer and solve it, which is the standard thing to do. So you can actually solve it numerically. Now, under certain simplifying conditions, this equation actually has an analytic solution, which is useful because if you really are interested in a certain kind of universe where you have, say, a dominant component, say in matter-dominated epoch, where you have matter which is dominating and dark energy maybe. So if you don't have to worry about radiation, for example, we are mostly interested in the matter-dominated epoch. So if you really don't have to worry about radiation and other components, you can, if you see this as a one-component universe, say just dark matter, so this h of a is just then given by expansion for just the dark matter. Or if you have dark matter and say dark energy. If you have these kind of simplifying scenarios for the background evolution, then this equation can actually be solved. Okay, so we'll see a simple way to solve this equation. Now, the first thing to note is we'll do it in two ways. There is a very interesting method which is originally suggested by Lemaitre, and then Zeldovich worked out elegant way of trying to find a solution to this equation. But before that, we'll actually use a brute force, a more algebraic and slightly not so elegant way of solving this equation. So we'll do that solution now, and in the afternoon class, we'll take the more elegant formalism by Zeldovich. It also has some insights into it. So first thing to note is that, so we are interested in dark matter, and if you take h of a, so we are interested in a certain kind of background model. So if I take h of a to be such that, so h square is just h naught square, and you take this as omega matter naught by a cube plus omega lambda. So this is our background model, say. So two components, this is like matter and lambda. So, and we have no radiation. That's very crucial. So please remember when this is useful. So there is no radiation. So if this is how h square behaves, then the first thing to show that h of a itself is a solution. Now this thing, let me just first write this down. So delta dark matter, as you know, is some x and t. So what we do is we split it And this is not always necessarily true that you can split it, but in our case, it does work. So we write it as some d, which is a function of t, times some function, which is a function only of x. Now this characterizes the spatial fluctuations, and you have a time dependency in the function d of t. So here it's a time equation. So we are basically, this equation is d dot dot plus twice h d dot equals to 4 pi g rho dark matter background and d. Now first thing to show is that the one solution d1 is actually this h of a. So d equals to h of a is actually a solution to this equation for a very specific kind of h of a, though, mind you. So if you have 1 by a to the power 4, it will not work. So for this two component universe, d equals to h of a is actually a solution that you can very easily verify. I will not go. So just substitute, instead of d, you substitute this h. You have to just take the derivatives, right? So you have h dot you have to find and h double dot you have to find, and you will see that it actually satisfies this equation. Now, h of a. So one solution is d equals to h of a. Now my question is, if perturbations evolved according to h of a, would structures form? Anybody has any suggestions? If the perturbations grew, or I don't know, evolved with h of a, then would there be structures? What kind of a function is h of a as a function of a? So d of a or d of t is say h of a. So question mark, will structures form?
I don't think no.
Why?
Because so h of a is basically the rate of expansion of the universe. So if a structure actually expand with the rate of expansion of the universe, then we cannot actually clump some regions. We cannot
You
get
just
some
look at
clump.
how it varies with time. This actually goes down with time. So instead of growing, it will actually decay. H of a is decay. It's going to decay. So if you start with some delta, it will actually fall if you plot it. So the known variation for h of a, you see with a, it is h of a at smaller a. At larger and larger a, h of a is smaller, right? Because there's 1 by a cube. So
Yeah,
at smaller
yeah,
a, h of a is larger. So it's actually fall. So instead of growing, this is going to decay. So this is actually called the decaying mode, which is of course fine, but this doesn't help
yeah, yeah.
us. So this doesn't help in formation of structure. So this solution has to be ruled out. Now it turns out this is second order equation. So there is one more. There's one more equation, one more solution to this. And to get this, we use a trick. So we say, okay, I mean, we'll use that Lemaitre's elegant method in the later class today. But let's just find an algebraic method to find this other solution. So what you do is you take this solution. You know that this is one solution, h double dot plus 2h h dot equals to 4 pi g rho bar a. This is just an algebraic way to do it. And then you have d double dot plus twice h d dot equals to 4 pi g rho bar d. And you combine these, okay? You combine these equations. So from the one solution you want to get, so you multiply the first equation by d and the second equation by h and subtract. So you have d h double dot minus h d double dot. Okay, let's see, plus twice h dh dot minus hd dot equals to 0. Now you see, what does this look like? This, you can write this as d dt of dh dot minus hd dot and plus, is it coming? Yeah. So dh double dot and minus, right, the other two terms cancel, and plus twice h dh dot minus hd dot equals to 0. You can multiply the whole thing with an a square, and this is just algebraic manipulation. And then you have this term becomes 2a square a dot by a. So one a cancel. Yeah. So it becomes 2a dot. 2a a dot. So this is 2a a dot times dh dot minus hd dot, the second term. And so this whole thing then can be written as ddt as of a square times this quantity. But this quantity is ddt of d by h. And then you have to compensate. So you have to multiply with a h square equals to 0. I'm just doing some algebraic manipulations. And you see from here, you get a solution because you see that I mean, of course, in this very, very specific case, this is not a general method at all. So you have a square h square times ddt of d by h equals to some constant. And you have then d equals to h integral of dt by a square h square. So this is another solution. So we obtain this other second solution. Of course, this if you, and I would urge you to actually work it out for the kind of Hubble Hubble parameters that you know for your standard cosmology, and try to plot this. And there's of course an overall constant which you can normalize it by choosing this value of d to be 1 at the present. So once you do that, you can actually show that this will actually be a growing mode in the sense that this will actually grow. So perturbations will actually grow under this. So I think I'll stop here because what I intend to do is take up this equation and solve using, first of all, the other method of Zeldovich, and then discuss the solutions into some details in different regimes. And then, of course, we have to look at the peculiar velocity. We are not looking at the spatial fluctuations right now. We are only looking at the time evolution of perturbations. So tomorrow onwards, we will look at study how the spatial fluctuations behave. So I think I will stop here and take questions.
Yeah, so please unmute yourself, and if you have any questions, please ask.
Yeah, Prakash, go ahead.
Yeah, okay. So my question is related to this source term. So you mentioned that gravitational potential is sourced by both dark matter as well as baryons, but the baryons contribution is less as compared to dark matter. Do you mean that this is at one particular scale? I mean, some larger scale? Because at small scale, say for example, at the core of the galaxy,
no. We, of course, we are looking at scales much bigger than the scales of a galaxy. So let's get some hang of the kind of scales we are looking at.
Mm-hmm.
So we are looking at cosmological scales. So a galaxy, and we are looking at redshifts, very large redshifts. The background densities, if you look at omega baryon as compared to omega dark matter, it's the comparison of that we are talking about. We are not looking at any very local variations. So for example, in the galaxy, you have a lot of H1. We are not talking about galactic scales at all. We are definitely not talking about. So we are looking at cosmological scales. And if you just know from your standard cosmology, what is the value of omega baryon and what is omega cold dark matter, then you will see one is much, much subdominant. So it's in that comparison that we drop that term.
Correct. No, I mean, the other thing is even on a large scale, do you see that wherever there is a dark matter, there is also baryon, or could there be offset between the two?
Oh, we'll discuss that. So right now we are not talking about baryons at all.
Okay, correct.
So I will have probably today's class, I will discuss a little bit of the baryons and how it's a very complex thing to study baryon. The whole 21 centimeter business is baryons, right? We are talking about the neutral gas.
That's
So
right.
it's an extremely complex phenomenon to study baryons because the gas undergoes so many astrophysical property. It undergoes evolution, not just because of cosmology, but due to a lot of astrophysics, right? Now, because of those astrophysical things, and because of the temperature variations and things like that, and pressure, so there's a lot of thermodynamics going on, right? So baryons are very tough to study analytically. So we'll see in what approximations we can actually make reasonable sense about baryonic physics. And those would be large scales and we can make some sense. But on small scales, I will argue, in fact, that you have to do numerical simulations to study H1.
Exactly, that's right.
So that's the whole point. So we will get some feel about what kind of things we expect, at least on large scales. But on small scale, we will definitely now have a good reason to argue why we definitely need numerical simulations. One would be nonlinearities. Other would be the essential complexities of baryonic physics, namely the dependencies of temperatures and other things. So, and if you talk about reionization, it becomes even more complex. So, yeah. So that is the whole subject. So that's the rest of the. So what I'm trying to do here in this course is just lay the framework of the dark matter physics, which is going to be strongly dominant in structure formation. So the basic structure formation is basically dictated by dark matter. So you will see that you begin with dark matter simulations.
And you consider only cold dark matter scenarios.
Cold dark matter, yeah. Again, cold dark matter. So you do cold dark matter simulations. And then on top of that, you start building up some baryonic physics. So that's the whole point. So how does the 0th order structures at least form using dark matter? So if you just have baryons in that small quantities, structures will not form actually. So dark matter plays a crucial role, and we can study dark matter, at least in the linear theory, quite well through these analytic perturbation methods. But we shall indicate the points where simulations become crucially important. And
the
why
other
we have
thing was related to this dark matter. So if instead of cold dark matter, if you take some other dark matter,
right,
say,
for example, warm dark matter.
Exactly, or any other. So do you think that the pressure term would be modified in that scenario?
Yes,
I mean,
it would. You have to do that. I mean, you have to. I mean, if it couples, I mean, here we are assuming that this is dark matter is not coupling with photons, for example, or any other species. So if there is some sort of coupling, no matter how weak it is, that will couple up the equations and make the whole thing even more complex. Now, what is traditionally done is one can always write down these equations and put them on a computer, and these would become extremely, simulations would become very, very complicated if you write the Boltzmann equations for everything and put every physics that you know. So what one does is one starts with cold dark matter and sees what kind of effects warm dark matter might have on because you typically don't want to, use the same thing at all scales, because certain physical effects will only dominate on certain scales. So one has to zoom into those scales and sort of incorporate it on top of a physics which is happening at a scale where these are not relevant. So if you apply everything try to do it on every scale, your numerics become very, very complex. So you actually look at it scale by scale.
So what happens in warm dark matter is they just suppress the power on some scales and then they do evolve the system, but then they do not change any equations of motion. So my question was whether that could be important or not. Yeah.
So when we study power spectrum, we shall see what kind of, so neutrinos, for example.
Correct, exactly. Yeah.
So we don't have species like neutrinos in our analysis. You can have things like neutrinos, which have some temperature, but so they would also have similar effects on the cold. But finally, we are interested in the cold dark matter power spectrum. How these other species affect the cold dark matter power spectrum, we can study that.
Thanks.
Fazlul, go ahead.
Yeah, hi. I hope I'm audible. My question is, we know that the cold dark matter is non-relativistic and it doesn't have pressure. So the formalism that we are doing, the Newtonian approach, so will it be applicable in larger scales also, horizontal scales?
It would be applicable on large scales, provided we are not going to scales which are horizon scales. I mean, then you would have effects of general relativity showing up. Those have some contributions. I'm not going through the details of relativistic perturbation theory because it's a very strong, robust formalism, and one can do that. One difficulty is you have to choose a gauge and work it out in that gauge. Now, the most physically convenient gauge is not, the formalism is not gauge invariant there. So you can take a gauge invariant formalism, but then it is not very physical. So there are difficulties in doing the full relativistic thing. There are lots of terms which come in the full relativistic equations, generative equations, which have contributions on very large scales, what are called horizon scale contributions. Now, if you're well within the horizon, if the kind of scales you're talking about are well within the horizon at the redshifts that you're talking about, then you really don't have to, these are good enough. These will suffice. You don't have to worry.
Okay.
So dark matter, the equations that you're talking about, the power spectrum that we will speculate from this formalism, will have good, I mean, most of the physics will be contained, even if we are well within, even if we are not so, not in much smaller scales. If it starts getting to the size of the horizon, then yes, then you have to take into account those terms from relativistic perturbation.
Sure. Okay. Thank you.
So, for example, if you do early universe physics, of course, the horizon is very small. So most scales are super horizon. So there you have to do relativistic. But at low redshifts, you don't have to worry about it so much. The scales of interest are mostly well within the Hubble.
Okay, one last question, Prashant, and
Yeah, Tapomoy. So you have been saying that if you have to choose the gauge the time, there is no direct choice of time. It's a different gauge, different time. Okay. So the T that you talk about here, what does that correspond to?
It's something which is something which is called if you want to map it to a relativistic formalism. So if you start with a relativistic formalism, then this would be in a specific gauge, you would get these equations in the k tends to infinity limit, which is very small scale. So that gauge is the synchronous gauge. So you can work in that gauge, and you will get these equations in the k tends to infinity limit. So it's fine. So this is one. But if you work in the conformal gauge, you won't get these equations. You would have other equations.
Right. And what is the connection of this time with the time in the?
And you can go from one gauge to another. All these, it's like writing Maxwell's equations, but finally the equations, the physics should not change, right? So
what
so
is
finally,
the connection of? Hello.
Yeah.
What is the connection of this time with the time in the space-like hypersurface and that you were talking about in FW times?
So here we are following the same. So here we are looking at co-moving, right? X dot X. So we are again looking at the local inertial frames and trying to patch them together. So the local inertial frames are getting patched. The global picture is very messy, of course, but locally we have the local free fall time, right? The co-moving, the coordinate system of the background universe. So we have you have your clock, and locally, if you think of it, that you align that, match that clock to the local surface, very small, of course, but then you sort of mesh it up. Of course, you won't get a global thing, but you can locally think of it. So we are using that same picture, the same picture as we do in normal cosmology. So as if there's a clock attached with the free falling objects.
It is the same time as that.
Yeah, but so that is why the synchronous gauge is very convenient, because it gives rise to these equations which are physically understandable. But this is not a gauge invariant formalism. In the gauge invariant formalism, you have these very nice gauge invariant quantities, but the equations are not, they don't, you can't make sense of them from your classical, from your Newtonian understanding. So that is the paradox. That's the thing. But this is very convenient. This gauge is good because it gives you some physical insight into these equations which you get. These are like fluid equations in some sense. Yeah. Was that your question? Do we have any other?
Actually, there are a few questions. So actually, we are running out of time. So
We can take one question maybe and first stop it. We'll just take one last question.
Okay, there's another question from Devala Mukhopadhyay. Why are the
Yeah.
viscous effects or the viscosities not taken into account?
Viscosity, as in you can take. Okay, you can take. You can write fluid equations. You can write in fact write equations for the theta and the rotations and all those things you can write. We will see. It's an interesting question. We'll see. In fact, those contributions, they die down. If you start with a perturbation, they don't grow. So we will see, for example, anything which has a rotational effect. For example, even a vector perturbation, any vector perturbation we will see will actually die down. You will not have those, they will not grow. So rotations here, these
hello.
things can be taken. Yes.
Hello, I'm Demal.
Yeah.
Am I audible? Hello.
Yeah.
So the thing is that you are analyzing the whole things depending on the first order hydrodynamics, or there are actually the first order hydrodynamics is not the stable one as what I know.
Yeah.
So to include the second order effect, so you have to have some viscosity change, viscosity effect or viscous effects. So that's why I'm asking that, is it interesting to consider them, or is there any general rule that you are taking, or just telling that is it dying down?
If you start with some initial, my understanding is it would, and I don't know if there are situations where they dominate. So I haven't come
Actually,
across.
in the book of the Weinberg on cosmology,
Yeah.
he has discussed on the bulk viscous effects on the structure formation when where you have considered the Robertson-Walker metric in his book. So that's why I am asking.
Yeah, you can definitely work it out. For example, but the question is whether that would be the full formalism. But the question is, are they going to make any significant contribution? I'm not sure. I can look it up.
Actually, I'm not sure. That's why I'm asking you.
Yeah, from my understanding is they don't make a lot of significant contribution to the kind of physics that we're looking at.
Okay. Thank you.
Okay, thank you all.
Okay, so what time shall we meet?
Let's meet at 2:30 again.
Okay, so I will start at 2:30.
Yeah. So if you have any questions, you can ask on that session or also in Slack. So let's stop this session and we will continue at 2:30. Thank you all. Yeah.
Okay.